Chapter 5 Simple Mixture. In this chapter, we're going to establish some mathematical equations of chemical potential for mixtures. And we're going to study Raoult's law, Henry's law, and the properties of solutions and the colligative properties. In the last chapter, we showed that the Gibbs energy change can be contributed by temperature change, pressure change, number of moles change. The molar Gibbs energy is called chemical potential. It is the chemical potential that determines the spontaneity of pure substance phase transition. So what about the mixtures? If you add 1 mole of pure water into a container of pure water, the volume change is 18.1 cubic centimeter. If 1 more water is added, the volume change is 36.2. So the volume change is simply number of moles times 18.1 cubic centimeter. 18.1 cubic centimeter is called molar volume, and molar volume is a property of pure substance. It's a constant. If you add 1 mole of pure water into ethanol, now a mixture is formed. The volume change is not 18.1, instead is 14. If 1 mole of water is added into the solution, the volume change is not 14 times 2. Instead, it's 29. So the contribution of volume from 1 mole of water is not a constant, but changes when the concentration changes. And this is called partial molar volume. Partial molar volume is a property of a mixture. Here is a plot of the partial molar volume of water in a mixture of water and ethanol. And when the ethanol concentration is 0, that means it's pure water, and the partial molar volume is the molar volume of pure water, which is 18.1 cubic centimeter. When the concentration of ethanol increases, the partial molar volume decreases. Okay, from 18 to 17 until 14 cubic centimeter. Now for pure substance, the molar volume is a constant, which is the derivative of volume over number of moles. In a mixture of A and B, the partial molar volume of A is the partial derivative of volume over number of moles A when B is kept constant. And the partial molar volume of B is the partial derivative of volume over number of moles B when A is kept constant. Partial molar volume changes with concentration. In a pure substance, the molar volume is calculated by the total volume divided by number of moles. So the total volume is the partial molar volume times number of moles. In a mixture of AB with a particular concentration XA, XB, the total volume is calculated by number of moles A times partial molar volume of A at this particular concentration, plus number of moles B times partial molar volume of B at this particular concentration. Note that the volume of the mixture cannot be calculated by number of moles A times molar volume of A. Molar volume of A, molar volume of B, these are the properties of the pure substance, not the mixture. So if you use this equation to calculate volume, and this volume is simply the sum of the volumes of the two pure substance, not the mixture. A simple question. A mixture contains 2.78 moles of water, 1.09 moles of ethanol. Okay, so it's a mixture. It is well known the molar volume of water is 18.1 and ethanol 58.9. Can you calculate total volume? Okay, to calculate the total volume of a mixture, you cannot use molar volume because molar volume, these are the properties of pure substance. We are now calculating the volume of a mixture. We need to know the partial molar volume of this mixture. The partial molar volume is a function of concentration. So first, you need to find the concentration of this solution. So we use number of moles of water, number of moles ethanol to calculate the concentration, okay, using mole fraction. So mole fraction of ethanol is calculated by 1.09. All right, that's ethanol divided by total number of moles. All right, so that's ethanol. Okay, we can also calculate water. Water is 1 minus 0.28. All right, so with that in mind, we use experimental data to find the partial molar volume of water and ethanol. So this is the diagram we showed in the last slide. So this is the partial molar of water as a function of a concentration. In this case, the concentration is 0.28. So 0.28 is somewhere here. All right, and we can find the partial molar volume of water for this concentration, 0.28 is 17.4 cubic centimeter. Similarly, we can use experimental data to find the partial molar volume of ethanol. All right, ethanol at this particular concentration, and we skip the steps, and the data is 55.6 cubic centimeter. So that is the partial molar volume of ethanol at this particular concentration. So with these two numbers, we plug into this equation. Total volume is the number of moles of water times partial molar volume of water, which is 17.4 at the concentration 0.28, plus 1.09 times 55.6, which is the partial molar volume of ethanol at this particular concentration. So add together, give you 109. That's the total. That's the volume of the mixture. Okay. Now, if you use the molar volume 18.1 and molar volume of ethanol 58.9 to calculate the total volume, you will get 115 cubic centimeter. And this is not the volume of this mixture. Okay, this is the volume before they mix, two pure substance before they mix, and 109 is the volume of the mixture. Partial molar volume is not the only partial molar quantity in a mixture. For instance, for pure substance, we have molar internal energy. In mixtures, we have partial molar internal energy. Similarly, partial molar entropy, partial molar entropy, partial molar Helmholtz energy, and partial molar Gibbs energy. We are going to see that in the next slide. The Gibbs energy divided by number of moles in a pure substance is the molar Gibbs energy. In chapter 4, we call this chemical potential. In a mixture, the chemical potential is the partial molar Gibbs energy. So the partial derivative of Gibbs energy over number of moles A when B is constant. And the partial molar Gibbs energy for B is the chemical potential for B. The partial derivative of Gibbs energy over number of moles B when A is constant. Note that the chemical potential A, B in the mixture changes when concentration changes. So for a mixture, just like the volume is the number of moles times partial molar volume added together. Here, the Gibbs energy is the number of moles A times chemical potential A, which is the partial molar Gibbs energy of A, plus number of moles B times chemical potential of B. The change of Gibbs energy is the chemical potential of A times number of moles A change plus chemical potential B times number of moles B change. Let's skip this slide. If you are interested, you can read a textbook about the more forms of chemical potential. Just like partial molar volume change with concentration, partial molar Gibbs energy, which is the chemical potential, also change with concentration. For example, for reactants A goes to B, at the beginning, the chemical potential of A is greater than B, so the reaction is spontaneously go from A to B. With time, more B is formed, and concentration of A decrease, and therefore their chemical potentials also change. Eventually, the chemical potential of A equals chemical potential of B. Reaction reaches equilibrium. And in this chapter, we are going to derive the equation to express chemical potential as a function of the concentration. In a mixture of two substances, 1 and 2, there will be two chemical potentials, mu1, mu2. And the two chemical potentials are related by Gibbs-Duhem equation. So if we know one of the chemical potential, then we can calculate the other. Next, we are going to derive equations for chemical potentials for mixtures. We start with the gas phase, and then we move to the liquid phase. And we also are going to see some applications of those equations. Let's start with the pure ideal gas. In chapter 3, we already showed that for ideal gas, the fundamental equation says delta G equals negative SdT plus VdP. If temperature is constant, then delta G equals VdP, and if we use ideal gas law, replaced by ideal gas law, integrate, we get delta G equals nRT ln P2 over P1. Now, if P1 is the standard state, then we have this equation. The molar Gibbs energy at a certain pressure equals the standard state molar Gibbs energy plus RT ln P over 1 bar. And the molar Gibbs energy is the chemical potential. So here is the equation for chemical potential of a pure ideal gas. The chemical potential, okay, equals the standard state chemical potential plus RT ln P over 1 bar. And this is the basis for all other equations. For a pure ideal gas, we just showed that the chemical potential is standard state chemical potential plus RT ln P over 1 bar. For a mixture, you have two substances, A, B. So for A, the chemical potential should use the same equation but replace pressure by partial pressure of A. Similarly, you should have a chemical potential of B in the same mixture should equals to the standard state chemical potential of B plus RT ln partial pressure of B divided by 1 bar. Okay? Now, if it's real gas, then we keep the form of these equations but change partial pressure by fugacity, which is the effective pressure, to make this equation still valid. With the equations we derived in the last few slides, we now can justify why mixing ideal gas is a spontaneous process. We're going to show that when mixing, delta G is less than 0, which is consistent with the second law. And the delta G is calculated by the Gibbs energy after mixing minus Gibbs energy before mixing. Three equations are important that we are going to use. One is that the total Gibbs energy is the number of moles of A times chemical potential of A plus NB times mu B. And how do you calculate the mu, chemical potential? If it's a pure substance, then it is the standard state plus RT ln P of the ideal gas. Now, if it's a mixture, then you use the chemical potential of A at the standard state plus RT ln partial pressure of A. Okay, same thing is for B. All right, so first let's look at before mixing. So before mixing, it's the pure substance, and so we use the second equation. And for A is Na mu A standard state plus RT ln P, NB mu B standard state plus RT ln P, the pressure of the pure substance. Now, after mixing, it's a mixture, so we are going to use the third equation. Okay, so here equation looks similar, but the pressure is the partial pressure of A and the partial pressure of B. So you use after mixing chemical potential minus before mixing of the chemical potentials. By doing that, you will see that all the standard state cancel each other. And let's combine the terms involves A. Okay, so it will be Na RT ln PA divided by 1 bar minus Na RT ln P divided by 1 bar. Okay, so we can factor out it's Na RT ln. Now, if you have two natural log, so if ln A minus ln B, you can write as ln A divided by B. So in this case, ln partial pressure A minus ln pressure should equals to ln partial pressure A divided by P. Okay, 1 bar cancel each other. And so that's the term involves Na. Similarly, you can calculate the term involves B. So the final equation here is NART ln PA over P plus NBRT ln PB over P. So in the next slide, we're going to show that the partial pressure of A divided by the pressure of the ideal gas, okay, equals the mole fraction in the mixture. So this is mole fraction of A in the mole fraction. And similarly, this is the mole fraction of B in the mixture. In the last slide, we show that when we mix two gases A and B, the Gibbs energy of mixing equals NART ln PA divided by P. PA is the partial pressure of A in the mixture after mixing. P is the pressure before mixing. Similarly, the B is NBRT ln PB over P. Now, if you mix two gases at the same pressure, and after mixing, the total pressure equals P. So this equation says the partial pressure divided by total pressure, and that is the mole fraction in the mixture. And therefore, our equation becomes NART ln XA NBRT ln XB. So now the question is this less than 0? Okay, to answer this question, we notice that XA, XB are both the mole fraction. Mole fraction is the number of moles divided by total number of moles, so it is less than 1. Okay, less than 1 and greater than 0. A natural log of a number less than 1 is always a negative number. Okay, so that means ln x must be less than 0. It's a negative number. So you add two negative number means delta G is less than 0. And therefore we proved that when we mix two ideal gas, the delta G mixing is always negative, and therefore the process is spontaneous. Here shows the plot of Gibbs energy of mixing of an ideal gas mixture. And we start with the pure substance A and B, and their Gibbs energies are set to be 0. According to the equation of the Gibbs energy of mixing, whenever you have a mixture, the Gibbs energy becomes negative, so it goes down, okay, on both sides. And the minimum is when the mixture becomes 50-50% in mole fraction. Now we know that delta G is contributed by two factors, delta H and delta S. Okay. Now for ideal gas, there's no intermolecular interaction, so when you mix two ideal gas, delta H is 0, doesn't change, and therefore delta G is only contributed by entropy change. A negative Gibbs energy means a positive entropy change. So in fact, entropy of mixing can be calculated by negative NR XA ln X plus XB ln X. So if you plot entropy, you got the opposite shape. So the before mixing, they are 0. After mixing, the entropy increase until it becomes maximum when 50-50% is reached. And so that tells us that the ideal gas mixing is spontaneous because the driving force is the increase of entropy. So whenever you mix two gases, molecules becomes more disordered, entropy increase, and that is the driving force for the spontaneity of mixing. We showed that in the gas phase, the chemical potential equals the standard state chemical potential plus RT ln partial pressure divided by 1 bar. So next we are going to derive an equation for liquid phase. But before we do that, we're going to introduce two equations. One is called Raoult's law, one is called Henry's law. These laws relate the pressure in the gas phase to the mole fraction in the solution phase. What is ideal solution? Let's compare with ideal gas. In ideal gas, there's no intermolecular interaction, only dots moving randomly in all directions. Now, real gas do have intermolecular interaction, and the consequence is form a liquid and eventually solid. So the fact that molecules form liquid is an evidence of the intermolecular interaction. In pure liquid of A, the interaction is between AA molecules. In pure B, the interaction is between molecules of B. Now, in a mixture of AB, there are different types of intermolecular interaction. It can be AA, BB, and AB. If all these intermolecular interactions are the same, this kind of solution is called the ideal solution. For an ideal solution, the partial pressure of a molecule A in the gas phase and the mole fraction of A in the liquid phase obeys Raoult's law, and that is the partial pressure of A in the gas phase is proportional to the mole fraction of A in the liquid phase times the vapor pressure of A when it's pure, and star represents the liquid A is pure liquid. So this is pure A vapor pressure. All right, this vapor pressure is determined by temperature. We have learned in chapter 4 that is the vapor pressure and the temperature is related to Clausius-Clapeyron equation. So that equation allows you to calculate vapor pressure of pure substance at a different temperature. Raoult's law tells us that in a mixture, the partial pressure in the gas phase not only depends on temperature, but also depends on the mole fraction in the solution phase. The more A you have in the solution phase, the more A can escape to the gas phase, and the higher the partial pressure in the gas phase. Also notice that in this equation, if XA is 1, all right, that means it's a pure A. And if you look at this equation, then the left side PA equals PA star. That means the vapor pressure is the pressure when it's pure, and the XA is 1 is the pure A, and so that is consistent. What kind of solution obeys Raoult's law? Raoult's law is for ideal solution where all intermolecular interactions are the same, and therefore only when the molecules are similar can they obey Raoult's law. Benzene and toluene solution is an example. Benzene and toluene are similar, have similar structure, and therefore they both obey Raoult's law. So if this is the benzene molecule, P partial pressure proportional to the mole fraction times its own vapor pressure when it's pure, and B is toluene, it also obeys Raoult's law. So the partial pressure is mole fraction of B times its own vapor pressure. Then the total pressure is when you add this together. Raoult's law is suitable for ideal solution where intermolecular interactions are all the same. Now imagine you have nitrogen dissolved in water. The solubility is so small that each nitrogen is surrounded by water. So the environment of this nitrogen molecule is totally different from the nitrogen gas itself. And therefore nitrogen does not obey Raoult's law. Instead, it obeys Henry's law. The Henry's law resembles Raoult's law in that both says the partial pressure in the gas phase is proportional to the mole fraction in the solution phase, but Raoult's law multiplied by its own pure vapor pressure, okay, pure A vapor pressure. But in Henry's law, it multiplied by a constant called Henry's constant. Henry's law is useful for very dilute solutions such as oxygen or nitrogen dissolved in water. Sample question. The Henry's law constant for oxygen in water is given, and calculate the solubility of oxygen with a partial pressure 190 torr. So Henry's law tells us that the partial pressure in the gas phase is proportional to the mole fraction of oxygen in solution times Henry's constant. So Henry's constant is given, partial pressure is given, and we can calculate the mole fraction of oxygen in the solution. So mole fraction is calculated to be 5.76 times 10 to the minus 6. And you can see this is a very small number, means almost 1 million water molecules, you will see one oxygen molecule. Now, for solubility, usually we use a different unit. For example, the molarity, okay, moles of solute per liter of solvent. Okay, so how do we convert this mole fraction to this molarity? Okay, to do that, we first realize the mole fraction is number of moles oxygen divided by total number of moles. And because the solubility is so small, we can approximate by saying it's moles of oxygen divided by moles of water equals 5.76 times 10 to the minus 6. If we know how many moles of water to form 1 liter, okay, so in other words, 1 liter of water, how many moles water? Then from this equation, we can calculate how many moles of oxygen in 1 liter of water, and that's the molarity. Okay, so to calculate the number of moles of water in 1 liter, we use volume, which is 1 liter, changed to cubic centimeter, times density, that gives you grams of water, divided by molar mass, and that gives you 55.6 moles. Okay, so we have 55.6 moles of water in 1 liter of water, and therefore the oxygen number of moles can be calculated, which is 3.177 times 10 to the minus 4. Okay, and that's the molarity of the solubility of oxygen. In a solution of A-B mixture, for A, suppose it's 98%, B 2%. The 98% is called the solvent, 2% B is called the solute. For A, because so concentrate, the environment of each A molecule is very similar to the pure A solution liquid, and therefore A usually obeys Raoult's law. Now for B, only 2%, so each B molecule is almost surrounded by a different molecule, so environment is very different, and usually B obeys Henry's law. Now if you have a solution, solvent obeys Raoult's law and the solute obeys Henry's law, this kind of solution is called ideal-dilute solution. Okay, so the A is ideal, obeys Raoult's law, and the B is so dilute, it obeys Henry's law. We are now ready to derive an equation for chemical potential in a solution phase. We start with gas phase because we know when liquid and the gas are in equilibrium, they have same chemical potential. And we also know the chemical potential of the gas phase, which is the standard state plus RT Lm partial pressure in the gas phase of A, all right, divided by 1 bar. But this equation is not what we are looking for a liquid, because we want to express chemical potential in terms of liquid property, such as mole fraction, instead of partial pressure in the gas phase. And this is when we are going to use Raoult's law. Okay, Raoult's law says partial pressure in the gas phase is related to the mole fraction in the liquid phase times its own vapor pressure when it's pure. Okay, so we replace the partial pressure by this product, so we have RT Lm PA when it's pure times mole fraction divided by 1 bar. Okay, now the natural log product can be separated. For example, if you have ln A times B, you can write it as ln A plus ln B. So in this case, this can be written as RT ln PA star divided by P naught. Okay, you separate this and plus RT ln XA. Okay, so the product can be separated, and therefore we have this equation: the mole fraction of the chemical potential of A in the liquid phase equals the gas phase chemical potential, which can be written as the standard state chemical potential plus RT ln vapor pressure when it's pure divided by 1 bar plus RT ln XA. Note that the chemical potential at the standard state is a constant. Even though we may not know the absolute value, we know it's a constant, okay, at a standard state, 1 bar. And also we know the partial pressure of A, not the partial pressure, the vapor pressure of A when it's pure depends on temperature. So if temperature is fixed, then the vapor pressure when it's pure is also fixed. So this is a constant, and therefore the whole thing here is a constant at a certain temperature. The only thing can change is the mole fraction. So when you change mole fraction, the chemical potential of A in the solution also changes. But the whole thing here is a constant. In the next slide, we're going to show you this has a physical meaning, and this is actually the chemical potential for pure A, liquid A, okay, when it's pure. From last slide, we showed that in a mixture of solution, the chemical potential of A equals the standard state A in the gas phase chemical potential plus RT ln vapor pressure of A when it's pure divided by 1 bar plus RT ln XA. Now compare this sum with the chemical potential in the gas phase, okay, standard state RT ln P pressure in the gas phase, and we notice that this is the vapor pressure of A when it's pure, and this indicates that this whole thing is the chemical potential for a pure A liquid, okay, because this is the liquid that is in the equilibrium with this pressure in the gas phase, okay, and therefore we can write the chemical potential of A in a liquid is the chemical potential of A when it's pure liquid. Now, because it's not pure, we add a correction, which is RT ln XA. XA is the mole fraction of A. When XA is 1, then this is ln 1 is 0, so the chemical potential of A in the liquid is the chemical potential of A when it's pure liquid. Okay, and we can think about this as a reference state or standard state. So the chemical potential of A at any condition equals the chemical potential of A when it's pure. But then you have to add a correction because it's not pure, and the correction is related to the mole fraction, is RT ln XA. With the equation to calculate the chemical potential in the liquid phase, we now can justify the mixing of liquid is spontaneous. And the procedure is similar when we justify mixing of gas phase. So we calculate the Gibbs energy before mixing, which is number of moles times pure A chemical potential. Okay, star means pure, so pure A, pure B chemical potential, that's the before mixing. After mixing, so we use the number of moles times mu A. Mu A is not pure, so we reference standard state is pure A, but then you need to time plus RT ln XA. So that's a correction. All right, that's the equation we derived from last equation slide. Similarly, the chemical potential of B in the mixture, you can write as a chemical potential B when it's pure. Okay, think about this as a standard state or reference state, plus RT ln XB. The delta G, the mixing, is calculated by final minus initial, and then you can see all the standard state, they cancel each other. Okay, so what we left is just RT ln XA, RT ln XB. Again, XA, XB less than 1, so natural log is negative, and we can prove delta G always negative. Okay, so delta G negative, and therefore the process is spontaneous. And again, just like the gas phase, we can prove that the driving force is the entropy increase. Okay, when you mix two liquid, a molecule becomes more disordered, so entropy increase, and that's the driving force to make delta G negative, to make a process spontaneous. We just showed that mixing ideal solution is always spontaneous. Delta G is less than 0. Now for non-ideal solution, we need to add an additional term that represents the difference between the intermolecular interaction. Beta measures the energy between AB molecule compared to AA and BB. When beta is very small, And from this plot, we can see the delta G is always negative. When you increase beta, and you can see the delta G increase until it becomes a positive number at the center. So 50% give you a positive delta G. That means mixing is non-spontaneous. You also see two minima, small minima, and that tells us that the solution separate into two solutions. One has a high concentration of A, the other has high concentration of B. So essentially, the mixing is non-spontaneous. Just like in real gas, we use fugacity or effective pressure to replace pressure to calculate the chemical potential of a real gas. In real solution, we use activity or effective mole fraction to replace the mole fraction to calculate the chemical potential of A in a real solution. The activity is the ratio of the partial pressure over the vapor pressure of A when it's pure. So for a pure solvent, the partial pressure of A equals the vapor pressure of A when it's pure, because there's no B in it. So the partial pressure is the vapor pressure when it's pure. And then according to this equation, activity is 1. So for a pure solvent, activity is 1. Now for ideal solution, then Raoult's law says the partial pressure equals the vapor pressure when it's pure times mole fraction of XA. And so we can see activity equals mole fraction. So ideal solution, activity equals mole fraction. If it's non-ideal solution, activity will be different from mole fraction. Sample question. The vapor pressure of 0.5 molarity potassium nitrate at 100 degree is 749.7 torr. What's the activity of water at this temperature? So activity is the partial pressure divided by the vapor pressure when it's pure. And the partial pressure of water in this solution is 749.7 torr. And what is the vapor pressure of water when it's pure at 100 degree? Well, it must be 1 atmosphere, which is 760 torr. So we calculate activity to be 0.9864. Just for curiosity, we can calculate the mole fraction of water for this solution because we know the molarity. So we can calculate the number of moles of water and potassium nitrate. So the mole fraction calculated to be 0.991. And you can see mole fraction, activity are close but not the same. We use activity to replace mole fraction for real solution. And one way to look at the deviation from ideal solution is to define an activity coefficient so that the activity equals mole fraction but times this activity coefficient. So when activity coefficient is 1, that means it is ideal solution because activity equals mole fraction. Okay, when gamma is 1. So if it's not the ideal solution, then the gamma will not be 1. So we can use this activity coefficient to represent the deviation from ideal solution. And then the activity now becomes the standard state plus RT ln XA plus RT ln gamma. Let's summarize the equations to calculate the chemical potentials. For ideal gas, the chemical potential of A equals the standard state of chemical potential A plus RT ln partial pressure PA divided by 1 bar. Now, if it's not ideal gas, we should use effective pressure or fugacity to replace the partial pressure of A, so that this equation is still valid for a real gas. Now, for solution, the ideal solution, the chemical potential of A should equals to the pure A chemical potential, liquid A chemical potential, plus RT ln XA. XA is the mole fraction of A in the solution. Now, if for real solution, we should replace mole fraction by activity, which is the effective mole fraction. Note that for gas phase, the standard state is 1 bar. Okay, the gas at one bar. Now, for solution, the pure A is considered to be the standard state. All right, so a non-pure solution A chemical potential, you can reference to the pure A and then plus RT ln XA. So in this way, all the equations for gas phase, liquid phase has the same format. The chemical potential equals the standard state chemical potential plus RT ln alpha. For gas phase, alpha is the pressure divided by 1 bar. For the liquid is the mole fraction or activity.